Today's speaker is Dr. Iván Díaz from the Weill Cornell School of Medicine. He is Assistant Professor of Biostatistics, working on methods for statistical learning and causal inference from observational and randomized studies with complex designs and data sets. And this work is at the intersection of statistical machine learning and optimal estimation in nonparametric models. Dr. Díaz received his PhD from the University of California at Berkeley and his master's and undergraduate degrees from the Universidad Nacional de Colombia. So thank you, Iván, for joining us today, and we're very much looking forward to hearing about how you use TMLE with time-to-event data.
Hey, thank you, Susan, and thanks everyone for joining in. So today this talk is going to be focused specifically on covariate adjustment for randomized studies. I will not focus so much as previous webinars have focused on the use of machine learning, although I will touch on that topic very briefly. But I'll basically focus on how to use parametric models for randomized studies. What's the correct way to use parametric models for randomized studies, and when you can and cannot, and how to do it properly, with a focus on time-to-event endpoints, as Susan said. But I will also briefly address the problem of ordinal outcomes, which is very similar to the problem of time-to-event endpoints. Brief outline. I'll start with, what's the rationale? Why do we want to use covariate adjustment in randomized trials? Then I will offer a brief critique of Cox proportional hazard models for randomized trials. Cox PH models are the most common method for analyzing time-to-event data, as everyone knows, and I'll sort of discuss why they are inappropriate for use in randomized controlled trials. Then I'll go on to discuss how TMLE actually can solve some of these problems that CoxPH has, and I'll go through a short example of TMLE for RCTs. And then I'll share with you a number of numerical studies where we look at the efficiency gains and all the reasons to use TMLE in randomized trials. So before I start, a brief acknowledgement to collaborators with whom I've worked on this topic. I've done work on this topic on and off. I started working on this topic many years ago, 5 or 6 years ago, when I was a postdoc at Johns Hopkins, working with Michael Rosenblum and Elizabeth Colantoni. Then I stopped working on this topic until a few months ago, when COVID-19 became the problem it is today, and so these methods became more relevant to the development of, or to the design of trials for COVID therapeutics. And so for that work, I've collaborated with David Benckeser, Alex Lutke, Dan Sharfstein, and Joe DeSigo. And a quick disclaimer that what I'm going to talk about today actually reflects my views and not necessarily theirs. So what's the problem and goals for today's talk? So we know that in covariate and in randomized trials, we need pre-planned adjustment. We need pre-planned analysis plans, basically. So if we want to adjust for baseline variables to improve efficiency in estimating treatment effect in primary efficacy analysis, this has to be pre-specified. The problem with covariate adjustment is that it is often misunderstood, it is underutilized, and it is underutilized and misunderstood particularly for problems with binary data, with ordinal data, and with time-to-event outcomes. These two latter types of outcomes, ordinal and time-to-event, are very common in COVID-19 trials. For example, the WHO ordinal scale, I think it's an 8-point ordinal scale of severity of the disease. And so the goals for today will be to describe estimands and covariate adjusted estimators for these outcome types, and to show you simulations based on real data that demonstrate the impact of covariate adjustment in real trials. So let's start with the first topic, why covariate adjustment. I'm going to use some notation throughout the talk, but I'll try to avoid it. The notation that I'm going to use is I'm going to use the capital letter T to denote the time to event that we're interested in measure. For example, in COVID-19, this can be time to intubation, let's say, for hospitalized patients. We're going to say that we're interested in assessing the effect of a binary treatment, and that binary treatment is going to be denoted by A. It can be an intervention, a drug, anything, any sort of therapeutic. And we're going to use the letter S to denote the survival function. So the survival function at time T within treatment arm lowercase a, right? So that's the probability that an individual or participant survives time lowercase t within treatment arm lowercase a. So because we're in the context of randomized studies, we don't have to, the causal effect estimation problem becomes much simpler. We have identification without assumptions. So in previous webinars, you've seen all the counterfactual notation. I'll skip that part because it's very trivial in the case of a randomized study. And I will just say that in a randomized study, causal effects are easily identified as contrasts between these two functions, between the survival probability at time t in treatment arm 1, and that contrasted with the survival probability at time t in treatment arm A equal to 0. Because of the symmetry, because we just need to contrast, so I'll just focus on estimation of this quantity of estimating the survival probability at T for any treatment arm A rather than the contrast. So this is what we call the unadjusted estimand, right? This survival probability within treatment arm A. Now let's talk about the covariate adjusted estimand. What is the covariate adjusted estimand? How is it defined? So to define it, I'm going to introduce some more notation, and I'm going to introduce the letter X to denote a vector of covariates that are prognostic of the outcome. So in the case of COVID, you can think of, let's say you're doing a randomized trial on hospitalized patients. You can think of age being, disease severity, viral load, age, comorbidities. That type of variable that we believe is prognostic of the outcome. We're going to assume for simplicity in the talk that this variable is discrete, but it can also be continuous, or it can take any form. And so a few probability calculations actually in here show this. So in the first line, I'm just using the sort of law of total probability, just saying, look, if you sum over values of x, the product of these probabilities, then this is equal to the survival function that we have here. And then in the second line, from the first to the second, I am using the fact that A is randomized, right? Can you guys see my mouse? Or no?
I don't see.
Okay. So I'm using, from the first to the second line, I'm using the fact that A is randomized, and therefore it is independent of X, to write the probability of X conditional A equals 1 as just the marginal probability of X. And so when you look at this expression is just the expectation of a random variable that's a function of X, right? So what we're doing is for every, so we have this survival, the conditional survival function, which is that a participant survives time lowercase t within arm A equals 1, and within strata of the covariates, x equals to little x. And so we take the expectation of that across the distribution of x. That can be written in this form here. And so this form, this expectation of ST1x, is what I'm going to refer to as the adjusted estimate. Right? It's a basic standardization, what I'm doing. So what happens in randomized trials is that the causal effect is actually identified by both estimates. As I show you quickly the math for why these two numbers actually should be equal to each other in randomized trials. And so these two representations of the causal estimate suggest two very different estimation strategies. So the first estimation strategy for the unadjusted estimate would be to use, what we know as the Kaplan-Meier estimator. We know this is the non-parametric estimator. We know it is, we know it has good properties. It's unbiased, et cetera, et cetera. For the adjusted estimate, the form of this estimate would suggest an estimation strategy in which we just fit a regression model for the time to event. So any type of algorithm that will give you a survival probability. This can be, for example, a Cox proportional hazards model, although of course I will talk about the limitations of that later, but it can also be a survival random forest fit, which is a recent development in the survival in the random forest literature. It can be basically any prediction algorithm that's able to predict for a treatment arm and for a covariate profile X, what's the probability, what's the survival function, basically. And so what we can do for the adjusted estimate is just to fit that model, obtain predictions by setting everyone's treatment level to 1, and then averaging that across the distribution of X. And so a natural question when you're faced with two competing strategies is okay, which strategy is better? How do I choose between these two strategies? And what we will see is that actually strategy 2 is better, the adjusted estimator is better, but the regression model has to be constructed very carefully so that we don't introduce model misspecification bias on the causal effect estimate. I'll address this model misspecification bias issue exactly later. And so, basically there are two main reasons why strategy 2 is better. The first one is we will have more efficiency. We will have estimates that have smaller standard errors in most cases. What this means is, this has very important implications both economically and ethically for trials. It means we will get answers faster because we will be able to have trials that recruit less patients, and we will have cheaper answers because of the same reason. And so that's a very important reason. Now, the second reason is that the covariate adjusted estimate is less sensitive to informative sensory. We'll touch on that also later. So let's sort of dive a little deeper into the first reason. The covariate adjusted estimate or covariate adjusted estimators can be more efficient. What is the reason for this? So in statistical theory, there is an element, or there is a concept called the efficiency bound. The efficiency bound is the smallest possible variance that any estimator can achieve. Any regular estimator, if I'm going to be rigorous, but you can think of any estimator. And so we want estimands that have a small efficiency bound, because those estimators are because then we can at least in principle construct estimators for those estimates that have a very small variance. And so what happens is when you study the efficiency bound for the adjusted estimate versus the unadjusted estimate, you can show that the efficiency bound for the adjusted estimate is always smaller or equal than the efficiency bound for the unadjusted estimate, right? So that's what sort of motivates covariate adjustment as a way to improve efficiency. Another property of the efficiency bound for the adjusted estimate is that it actually gets smaller and smaller as it decreases as the predicted value of X increases. So the more predictive X is of the outcome, the smaller the efficiency bound, the better standard errors you can get for your estimator. So these two are sort of the motivation for using covariate adjusted estimators in randomized trials. A quick, sort of intuition for efficiency gains. Why and how do these efficiency gains happen in randomized trials? You can actually see it from these two lines of math that I had showed you before. And the reason, at least the way I conceptualize it or the way I like to understand it, there are other ways, of course, this is not the only way, but if you want an intuitive explanation for why the efficiency gains are happening, they are happening because if you look at these two expressions on the right-hand side, in the first one, we are estimating the distribution of the covariates, the baseline covariates, conditional on each treatment arm, right? So we're going and first estimating them on the treated and then estimating them on the controls. What the adjusted estimand does is that it uses the information that the treatment is independent of the covariates, and it actually estimates that distribution pulling across treatment arms. So that means a much more efficient estimate, possibly using twice as much data, a much more efficient estimator, of the marginal covariate distribution. So I think that's where at least that's one way to conceptualize how these efficiency gains are happening, by just pooling data and using the fact that treatment is randomized to pull that data and estimate covariate distributions. So that's sort of the motivation for covariate adjustment for efficiency gains. Let's talk a little bit more about now the motivation for reliance on the assumption that censoring is non-informative. So in some randomized trials, you have loss to follow-up, right? It usually happens. The extent to which it happens, it can be controlled in the trial design phase, but it usually does happen. And so let's take a closer look at what each of these estimands and estimation methods assume for censoring. So I'm going to introduce some more notation. I'm going to use capital C to denote the censoring time. And what the Kaplan-Meier estimator assumes, and really any unadjusted estimator, is that treatment is independent of censoring within treatment arm, right? So it does allow for treatment to be a common cause of the time to event and censoring, but it does not allow for any other common causes of the time to event and censoring. In contrast, adjusted estimators, and really this is just an identification issue, but adjusted estimators assume that the time to event is independent of the censoring time within strata of not only the treatment, but also within strata of the baseline covariates. Right. So this can potentially accommodate is a much weaker assumption than the assumption made by the Kaplan-Meier estimator. So, for example, you can think of cases in which poor health status at baseline might mean that a participant is more likely to miss follow-up visits, but it's also more likely to develop the clinical endpoint. So you can actually adjust. You can now adjust for informative censoring from variables that were measured at baseline using adjusted estimators. This problem would not be, we couldn't deal with this problem if we use unadjusted analysis. So that's another reason to prefer adjusted analysis in randomized trials. So we've talked about the reasons for why we should adjust in randomized trials, and now I'm going to move to the question of how do we adjust, right? And whenever we talk about models, as I said before, whenever you see a survival probability or whenever you think as a statistician or a classically trained epidemiologist or classically trained statistician, what you think is, well, I have a time to event outcome and I have a treatment and I have a set of covariates. I'm going to fit a Cox model. That's the sort of to-go covariate adjustment or like modeling approach that we all have been trained on doing. So I'm going to briefly talk about what are some of the issues of actually doing that for randomized trials. So what common practice would suggest is, you go and fit your Cox model. You don't include interactions. I think this has been also discussed in other talks in this webinar. You don't include interactions. You just put your treatment and the covariates, and you take the coefficient in front of treatment, and you interpret that coefficient as the log of a hazard ratio, right? And so that's what people commonly do, and this slide is a critique of that practice. So the first one, the first thing that you need to be aware of is that Cox-PH models estimate a conditional hazard ratio. Right? And so the first question that you have to ask yourself is, well, is a conditional parameter really the answer to the scientific question? Am I interested in effects within strata of all the covariates, right? And you have to put this in context of the randomized trial that you're looking at. For example, what if in some other part of the world, a randomized trial is being carried out for exactly the same question, exactly the same treatment with exactly the same time to event endpoint, but the analysts of that trial or the people who designed that trial decided to adjust on a different set of confounders that just because they had availability to more or less data. Do we really does the treatment effect in these two trials should the estimands differ, right? So that's an important first thing to take into account. There are other critiques of the hazard ratio as an effect measure. Miguel Hernan in this article, The Hazards of Hazard Ratios, lays them out very nicely. I'm not going to talk about them so much, but I am going to say a few things about hazard ratios in Cox models. The first one is that estimands are only defined within the model. In this case, if the model is incorrect, we don't know what we're estimating. We're possibly estimating some average hazard ratio or some other thing, but we don't really know. So we have to really think about what we're estimating if the model is misspecified, as it usually and most certainly is. And as I said before, we seldom believe these models, so the standard errors of these models are going to be incorrect. We don't know what we're really estimating. And so the question the natural question that comes up is, well, why should we, when we're in a randomized trial, why should we introduce all these issues of model misspecification bias or of interpretability of the estimates, where this modeling is unnecessarily in principle, where we could just have gone and used the Kaplan-Meier estimator and get an effect, an effect estimate that relies on no assumptions. A lot has been written about this, but I just wanted to bring it up, because even though there has been progress in covariate adjustment for randomized trials, it is still very common that people in their statistical analysis plans, they propose to use a Cox-PH model for analysis, and I think that is very problematic for these reasons and others. However, I mean, that is not to say that you cannot use Cox-PH models in a randomized trial, but just you have to do it carefully, as I will explain below. So exactly, okay, how do we solve this problem? How do we solve the problems of Cox-PH models in randomized trials? How do we do covariate adjustment correctly? So the first thing that we have to address is the problem of defining the estimate, right? We don't let the model that we are using define the estimate that we're interested in. We define the estimate beforehand and then fit models or use estimation techniques that are appropriate for that estimate. And so, for example, for time to event outcomes, there are a few estimates that you can use. I'm just writing 3 of them here, but there are more. The first one is the restricted mean survival time, where for some restriction time tau, you're concerned with estimating what's the expectation. Let's say we're talking about a time in days. So what's the and let's say tau is something like 30 days. If you're looking, for example, at the effect of, again, the running example that I've been using, some drug for hospitalized COVID patients, and time to event is time to intubation, let's say. So tau is 30 days, right? So you're interested in looking at the mean time to intubation in the first 30 days for patients who are treated versus the mean time to intubation for in the first 30 days for patients who are in the control arm, right? So that's the interpretation of the restricted mean survival time. And again, this is entirely model-free. You can also use risk difference, right? So you can also say, okay, what is the difference between in probability that a patient remains intubation-free by 30 days in the in the treatment versus the control arms, right? So that's another estimate that's possibly of interest, or you could just compare the 2 probabilities in terms of a ratio instead of a difference. So that's the first solution that we need to use. Just define the estimate upfront. Don't let your modeling approach define the estimate. The second problems introduced by Cox models, the problems of introducing model misspecification bias into the analysis, can be dealt with by using doubly robust estimators, right? So, such as TMLE, which is the method actually that we're going to discuss. So, I'm sure in previous talks, you've seen previous webinars, you've seen that doubly robust estimators are unbiased, where I'm using the term unbiased a bit loosely here, but I just mean bias that disappears very fast as sample size increases. These estimators, the doubly robust estimators, are unbiased if at least one of these 2 conditions hold. The first condition is that the survival function conditional on treatment and covariates is consistently, that means correctly estimated. And the better, that the model that we pose for estimating that survival function is correct. And then the second condition is that the treatment mechanism, so the probability that you're in the treatment arm conditional on covariates, is consistently estimated, right? So as long as one of these 2 conditions is correct, we have an unbiased effect estimate if we use a doubly robust estimator. So the advantage here is that in randomized studies, we know that the treatment mechanism is consistently estimated. So this condition 2 will always be true, no matter, well, as long as we use a relatively clever model for the probability of A conditional on X, like let's say a logistic regression model with main terms only, for example. That would be a consistent estimator for the treatment mechanism, because we know, let's say you're not doing any, let's say it's just, the randomization is the flip of a coin. So we know that the intercept is positive, and we know that all of the other coefficients associated to all the covariates have to be 0, or, are 0 in the population. When you actually perform estimation, they might be a little different because of chance imbalances. But we know that that is a correct model for the treatment mechanism. So the key point here is that doubly robust estimations provide a framework to obtain efficiency gains from covariate adjustment while avoiding introducing bias due to model misspecification. So you can actually go and use your Cox model now, as long as you're using it in the context of a doubly robust estimator, so that we don't introduce model misspecification bias. So let me now move on to a simple example of how TMLE happens for randomized controlled trials. And to make the example a little simpler, I'm actually going to switch for a second to thinking about ordinal outcomes. Again, the problem of ordinal outcomes and time-to-event outcomes, at least discrete time-to-event outcomes, is very similar, because a discrete time-to-event outcome is like an ordinal outcome, right? So we're going to use some notation Y now, and we're going to say Y is an ordinal outcome that can take possible values 1 through capital J, right? And so a typical model, instead of the Cox proportional hazards model for this problem, would be the ordinal logistic regression model, which assumes proportional odds. So we're going to work with that model. That model, in the context of ordinal outcomes, suffers from exactly the same drawbacks as we explained above for the proportional hazards model. It has exactly the same problem, and I'll show you exactly where the problems come, like in the estimation procedure. So for when we have ordinal outcomes, in complete analogy to the survival case, we're interested in estimating a treatment-specific distribution. So what we're interested in this case is to know this function f, which is what is the probability that the outcome is smaller or equal than j, conditional on each treatment arm, right? And then any contrast of these treatment-specific distributions will give me a causal effect. One of these possible causal effects is, which could be of interest, is the Mann-Whitney estimand that I wrote down here in terms of the distributions. It's just, you have to get the densities as well, the probability mass functions actually, and to just do some contrast. But actually, I mean, the math, I'm omitting it here, but you can actually show that this estimand can be interpreted as the probability that a random treated participant has a better outcome than a random control participant, right? You can argue, again, for any other estimand, as long as it's well defined as a contrast of these distribution functions. And the Mann-Whitney estimand that I'm showing here is just an example. But I'm going to focus on estimation of the treatment-specific distribution FJA. And so for simplicity, let's assume that randomization is 1-to-1. So we have, a randomization probability of 0.5. And I'm going to use f hat at JAX to denote an estimator of the conditional distribution of the ordinal outcome within treatment arm lowercase a and within covariate strata lowercase x. For example, let's assume for now that estimator is obtained from fitting an ordinal logistic regression model, as I explained above. So one can actually show that the adjusted estimator that I described earlier, where you just take that model, right? Make predictions by fitting by fixing the treatment level to lowercase a for all the subjects. You take your model, make your predictions, and then just average those predictions across the sample to estimate the outer expectation in the formula, in the G computation formula that I showed above. You can show that an estimator written in this form is doubly robust if it solves this estimating equation, right? Actually, that is you might have seen TMLE from other angles in this webinar series, but this is what TMLE is doing at bottom. It's taking a this is what the machinery is doing. It's taking an initial estimate and it's estimate of the regression function, and it's making sure that it solves an additional estimating equation that endows it with very useful properties like double robustness, right? So in this case, because the treatment mechanism is known, 0.5, we wouldn't need to estimate it. It will turn out that estimating it is actually better, but in principle, we wouldn't need to estimate it. We can just plug it in here in the denominator, 0.5. And so all we need to solve now are these score equations, right? So what do we have in these score equations? We have the outcome. So the outcome of this regression model is just the indicator that yi is smaller or equal than j. That's what we're modeling. Then we have the predictions, so the f hat at j lowercase a and xi. So this within curly brackets is just a residual of the regression. And then this other term, the indicator that ai is equal to lowercase a over 0.5 is just the clever covariate that you have probably seen many times already in TMLE. So for this problem, if we want to estimate all these treatment arm specific distributions, we actually have to solve these equations. We need a TMLE that solves these equations for all values of the outcome, for all j, right? And so, of course, this 0.5 comes out of the equation, so we're left with only the indicator of, or comes out of the sum, and then you can get rid of it in solving the equation. And so we're left with a clever covariate that's just the indicator of ai equal to lowercase a. So now so this is what we want to achieve, right? In this slide, I told you, look, this is what we want to do in order to get estimators that are correct, or in order to get at least one estimator that is correct in randomized trials. Now let's look at what vanilla ordinal logistic regression would do, right? So what would you do if you just go and fit a vanilla ordinal logistic regression? Well, the model is this. The model is the first equation that I have in the slide here, and it would just say, well, I have intercepts for each category of the outcome for each of the ordinal categories. Then I have a parameter beta that accompanies A and a parameter gamma that accompanies X. And so you can actually show that if you fit this with maximum likelihood, for example, the score equations that are solved by this model are these two, at least the score equations associated to alpha, j, and beta. I'm omitting the score equation associated to gamma because it's not of interest here. But the score equations that are associated to alpha, j, and beta are these two, right? So for each j, we have the first equation. So we do have this residual term here that we had in the previous slide, which is the one we need to solve. And the second equation is this one where we do have the residual term. We also have the clever covariate, the indicator that ai is equal to a, as we needed before. And we're summing over all I. But in this second equation, we're not actually solving the equation that we need to solve because we're summing across all lowercase j, right? So that's a problem. So bottom line is the vanilla ordinal logistic regression model is not solving the estimating equations that we wanted to solve so that it is a double robust estimator. Luckily, this has a very easy fix in the case of ordinal logistic regression. All you need to do is you actually need to fit separate models for the treatment and for the control arm. If you fit separate models for the treatment and for the control arm, what you're doing is that this first equation associated to the intercept is getting solved. Is solving the relevant estimating equation that we wanted to solve for the TMLE. Right? So basically because when you're doing this sum over I is equal to 1, from I is equal to 1 to n, and multiplying by the indicator that ai is equal to little a, you're effectively restricting the sum only to those who have treatment level equal to lowercase a, right? That restricting that sum is equivalent to just stratifying. Consider a subsample in which you have only the participants that were in the treatment arm or in the control arm, right? So quick, easy solution. In a randomized trial, you have an ordinal logistic regression. If you want to use, vanilla ordinal logistic regression and you want it to be a TMLE, all you need to do is fit ordinal logistic regression separately for the treatment arm and for the control. So while this is a solution to the problem, this is not the best solution to the problem, right? This is sort of a workaround to say, look, you don't want to go all the way to TMLE, just want to, a quick fix for your model misspecification bias, you do this. Now, if you want to, you can actually show that you can do much better by fitting the treatment mechanism, as I explained before, rather than plugging in the 0.5 in this in the clever covariate. So what this would entail is actually you have to go now and fit a proper TMLE to this problem instead of just fitting two separate ordinal logistic regressions. But of course, I mean, this is one step much better than just fitting a vanilla ordinal logistic regression, this stratification approach. So as I was explaining below, another TMLE approach, so going one step beyond in improving the estimation procedure, would be to first, of course, do the same stratification, fit an ordinal logistic regression model separately for the outcome for the treated and separately for the controls. But now you can fit a weighted ordinal logistic regression model, right? And you can use weights. Like I don't know if you've seen this, but in TMLE you have two different ways of using the clever covariate. One is as an actual clever covariate, and the other one is using it as weights in the loss function. So I'm taking here the second approach. So you can actually fit the model for treated participants with weights equal to this inverse probability, where this p hat again may come from a logistic regression, and the model for the control participants would be fitted with this weight, where again the p hat is the same, and this is just what I said before. P hat, the probability that A is equal to 1, conditional on W, and I'm sorry, I mixed my notation here. I actually mean X when I say W in this slide. But yeah, it's just W is just the clever covariates. This may be a logistic regression fit as opposed to just 0.5. And there is actually theory showing that this estimator is expected to have even more efficiency gains compared to the previous simpler estimator that just plugged in the 0.5 for the propensity score. So that's two, simple TMLEs that you could implement for this problem. There are some other considerations. There are some other things that we have to take into account for this problem. The first one is that when you have loss to follow-up, and the loss to follow-up is non-trivial, like, you have more than, say, 5 or 10% patients who are lost to follow-up, then the problem becomes effectively an observational study. You can't rely so much on randomization anymore because loss to follow-up might be informative. So you actually now need to start using doubly robust estimators that actually exploit the full advantage of doubly robust estimators, which is that you can get either the model for the outcome or the model for censoring misspecified, but not both. And as you've seen in many other talks, TMLE plus machine learning can aid in getting, in ensuring that you're getting the right fit for either the outcome model or the censoring model. So this is a very, very big important caveat. If the trial is expected to have loss to follow-up or missing outcomes, using parametric models is likely to hurt you, because you're very unlikely to get the double robustness that you need. Because again, the censoring mechanism that you fit with a misspecified parametric model will be not consistent, and likewise for the outcome regression. So in studies where you have loss to follow-up, you need to start incorporating machine learning. The other point, which is It's half of a more like theoretical, sort of esoteric point that is not so common in practice, but it does happen, is that when you are using doubly robust estimators, like the estimators that I described above, you can actually lose efficiency if your model is severely misspecified, right? If the outcome model is severely misspecified, you can actually lose efficiency compared to the unadjusted estimator. So that is a big, important sort of theoretical problem. Again, I haven't seen that so much in practice, and when I try to generate data, to simulate data to make this happen, you have to work hard to actually find data generating mechanisms and model misspecifications for which this happens. But it is a problem. It is a theoretical problem. And so as a solution for that problem, we have actually developed estimators that have guaranteed efficiency gains, right? We have developed a number of estimators for time to event, ordinal, and binary outcomes that are guaranteed to have a variance that is smaller or equal than the variance of the unadjusted estimator, right? So here are three papers that do this explicitly for the first one is for binary outcomes. That is not a paper of mine. It's a paper by Michael and Elizabeth, Michael Rosenblum and Elizabeth Colantroni. The second two papers for ordinal outcomes and for time to event outcomes are mine. Very important here to note that these papers are focusing on the problem of randomized controlled trials, but they rely on ideas that existed, much longer before us. Like I think some of these ideas go back to the original TMLE paper in 2006. So these three papers just reap the benefits of the TMLE framework to actually put this in context. So some of the ideas are new, but definitely the framework is not. And so let me just briefly give you an overview of what these methods that have guaranteed guaranteed efficiency gains are doing. The key idea is that we know that inverse probability weighting for sure improves the efficiency compared to unadjusted estimators, right? We know that. So the question is, can we actually take the TMLE and make it so that it looks like an IPW? Can we construct a TMLE that has, in addition to an outcome regression estimator expression, it also has an IPW expression? And so basically this is what we do. What we do is we find a way to make the TMLE also have an alternative representation as an IPW, and that involves solving some additional estimating equations. The theory of how that works is in the papers that I described above, but I'm not going to go into detail. So that estimator turns out to also be doubly robust, and in particular, it is the most efficient estimator. It has the best possible variance, the efficiency band, if the model outcome, like the outcome model, is consistent. So I'll stop the theory there, and I'll use the next 8 minutes that I have left to actually talk about some numerical studies. So we used a number of trials to generate data sets to actually see how these estimators work in practice with real data. So the first trial that we used is the MISTI-2 trial. Actually, I did this work, again, as I said, 5 or 6 years ago when I was a postdoc at Johns Hopkins. By now, the results of the MISTI-3, the phase 3 trial have come out, but I'm going to show the results with the MISTI-2 trial. So this was a trial on ICH, intracerebral hemorrhage, that was testing a novel surgical procedure that was minimally invasive versus standard medical care for removal of the clot. The outcome was the modified ranking scale, which it measures disability from 0, which means no disability, to 6, death. And we had 3 baseline covariates that were prognostic, which were age, ICH volume, so the volume of the area of the brain that was affected, and NIH stroke scale. So actually what we saw in this trial is that we expected efficiency gains of about 25%, a reduction of about 25% in sample size. We also used the ABC trial, which had 415 patients who were diagnosed with stage 3 ovarian cancer. There were two therapies that were being tested, intravenous only versus intravenous abdominal catheter chemotherapy. In this trial, the endpoint was survival time measured in days. Again, we had three baseline variables that were prognostic: age, SOFA score, SOFA score, which is a measure of the organ function, and the Apache score, which measures the severity of the disease. And for this trial, we found a sample size reduction of up to 3%. Most importantly, for this trial, we had right censoring, and so the Kaplan-Meier estimator might have been inconsistent. The CLEAR-3 trial is a phase 3 prospective trial with around 500 patients that had IVH. So this is a hemorrhage in the brain ventricular system. And again, the comparison was between a novel procedure and standard medical care, again, for covariates that are prognostic. And in this trial, we saw a sample size reduction of up to 15%. So as I said before, I'm just briefly describing here how the simulation happened. Our objective was to mimic as closely as possible characteristics of the true data generating mechanisms. So the way we did that was by actually resampling pairs of time to event and covariates X, right? So we like a bootstrap sample, we resampled T and X and randomly generated A independently. So the treatment variable is generated randomly. In these simulations, we used actually effect sizes of 0 and an effect size that was equal to the TMLE estimate in the real data. And data for the positive effect case was generated by adding a random variable to the observations that were treated. This random variable was independent of everything else. And so we actually also looked at two cases for prognostic power. So what is the prognostic value of X and T? So the first one is as observed in the data, so that corresponds to the resampling that we did. And the second one is a prognostic power of 0, which is obtained by actually doing the process I described before, but randomly shuffling the covariate values. And we also censor patients according to a parametric fit to the data. So here are the results for the case where we have the predictive power that was actually observed in the data. We have the 3 studies in the rows. I'm comparing 4 estimators: the unadjusted, which is the Kaplan-Meier, the IPW estimator, the augmented IPW estimator, and the proposed TMLE that has efficiency guarantees. I'm showing the results in terms of bias and relative mean square error. So this relative mean square error is the squared error of the unadjusted over the mean square error of all the other estimators. And so we're looking in the first set of results at a case where the effect is 0, and in the second set of results at a case where the effect is equal to the effect actually observed in the sample, in the trial. And so what we see is, like, for the MIST trial, we would have seen efficiency gains of 31% for the observed effect, 39% if the effect had been 0. So basically, this really shows you the power of covariate adjustment. If you do covariate adjustment with just the IPW, you're still doing much better than using just the unadjusted. However, by using a double robust estimator, such as the augmented IPW and the TMLE, you actually increase efficiency gains by a little, by 2% or 1% in some cases. So this is a nice illustration. Now, what happens when there is no prognostic power? In the case of no prognostic power, the problem is that we know that asymptotically, as we get more and more a larger and larger sample size, these two estimators, the unadjusted and all of the adjusted estimators, should be identical. They should have exactly the same variance because X is not adding anything to the prognostic power. However, in small samples, it can happen that actually adjusting for covariates can hurt us, and that's what we do see in these trials. We actually get efficiency losses of about 2%. However, we believe that these efficiency losses of 2% are actually, worth it in light of the huge efficiency gains that we might get. And also, it usually will not be the case that we're adjusting for covariates that are not prognostic. There's usually background knowledge to actually only use covariates that are prognostic for sure. So I think I've discussed this. In the last minute, let me talk about a simulation that we also did with COVID data. So we actually took, for COVID data, we don't have an actual trial, so we just resampled patients that we saw here in the New York search that happened in March. So we took patients hospitalized at Weill Cornell Medicine, New York Presbyterian Hospital prior to March 28, and we simulated sample sizes of 100, 200, 500, and 1,000. Again, we did a simulation similar to what I showed before. I'm going to skip the details of these, but you can read them later if you are so inclined. And we saw these results. So when the treatment effect is 1 day for these different sample sizes, we actually see efficiency gains of up to 20% for assessing efficacy of a treatment in COVID. So I think this is very powerful results, particularly now that so many COVID trials are being developed. So lastly, let me conclude. We're at the top of the hour, so let me conclude with just there is software for this. You don't have to go and code it yourself. There's software that's implemented. The first and the last packages are packages I developed. The first package is not as well maintained, but the second one is. The second package was developed by David Benckeser. It's a great package. It has plot functionalities. You can go ahead and use it and play with it yourself. And we're also working on improving so the first two packages are for ordinal outcomes. The last package is for survival outcomes. And again, you're welcome to use them, and I'm happy to provide feedback on their use. And with that, I think I'll end. Thank you.